Hello everyone, my name is Siddesh and today I'm presenting my master's research project titled Performance Comparison of AWS Lambda and Azure Functions using Spring Boot and Quarkus Java Framework. So this research was conducted under the supervision of Rashid Majumbi at National College of Ireland. So over the last decade, serverless computing, especially function as a service, has changed the way we think about application deployment. Instead of managing servers, scaling configurations, or infrastructure, a developer can simply deploy code and let the platform handle everything. Platforms like AWS Lambda and Azure Functions are leaders in this space, offering automatic scaling, a pay per execution pricing model, and reduced operational complexity. But when we bring Java into this environment, a challenge emerges known as the cold start problem. Java applications rely on the JVM, which requires time to initialize. Framework like Spring Boot add even more startup weight. This means the very first request after a period of inactivity can be noticeably slow, which impacts user experience, especially for latency sensitive systems. In contrast, Quarkus is a modern cloud native Java framework designed specifically to solve these issues by reducing memory usage and improving startup speed using techniques like ahead of time compilation. This creates a critical question for developers. Which combination of framework and serverless platform actually performs better in real world conditions? Specifically, how do Spring Boot and Quarkus compare when deployed on AWS Lambda and Azure Functions? This question forms the basis of my thesis. Looking at the existing literature, several patterns clearly emerges. First of all, almost all researchers agree that cold start latency remains the biggest challenge in serverless computing, especially for the language like Java. Second, due to JVM's architecture, a traditional Java framework struggle in serverless environments, especially compared to the languages like Node.js or Python. Third, Quarkus has shown impressive performance in microservices and containerized environments, often outperforming Spring Boot in terms of startup time and memory footprint. However, while many studies compare this framework in Kubernetes or containerized deployment, there is no existing direct comparison of Spring Boot versus Quarkus on both AWS Lambda and Azure Functions together. So, in summary, the gap is that we do not know how these frameworks behave in the true functional service model across multiple cloud platforms. My research aims to provide a clear experimental comparison. To address the research question, I've designed a controlled quantitative experiment. I've built four separate serverless applications, all performing the same simple CPU bound operations. Spring Boot, which is deployed on both AWS Lambda and Azure Functions, and Quarkus, which is deployed on both AWS Lambda and Azure Functions. So the motivation behind this research is simple but crucial to help the developers and architects make data-driven decisions when selecting their serverless technology stack. To ensure a fair and accurate comparison, I followed a strictly controlled methodology. The key principle was to create an intentionally minimal application, essentially a tiny microservice, so that performance differences would be due to the platform and framework themselves and not the application complexity. So let me walk you through the project structure. So I have organized everything into a modular automated system. The project contains four main application directories, the Spring Boot AWS Lambda. It uses a Spring Cloud Function AWS adapter with a function interface that implements request handler for API gateway integration. Spring Boot Azure Functions. It uses Azure Function Java SDK with HTTP triggers and anonymous authorizations. Quarkus AWS Lambda. It uses Quarkus Amazon Lambda extension with a lightweight request handler implementation. Quarkus Azure Function. It uses Quarkus with Azure Functions annotations. So as you can see, I've built a fat jar, and this jar is used to deploy on the serverless architecture. Each project contains Maven POM configuration of it includes Maven POM configurations optimized for serverless deployment. Spring Boot uses the Maven shared plugin to create deployment ready jars, while Quarkus uses its specialized Maven plugin for both JVM and native compilation options. I have developed four identical implementations, each So I have developed four identical implementations, each containing a single get endpoint. This endpoint performs the exact same lightweight computations. It sums number from 1 to 100, multiplies it by 2.469, and returns a JSON response with a timestamp and metadata. So no databases, no authentication, no external integration, just pure serverless function execution. All the four implementation use Java 17 and are configured with 512 MB memory and have a 30-second timeout. The application code is nearly identical across all versions with only framework-specific adaptations for AWS Lambda handlers and Azure function triggers. To automate this process, I have made multiple scripts. So the build all script, it compiles all four projects sequentially, reporting build times and success status. On my development machine, the complete build cycle takes approximately 86 seconds. The deploy all script, it orchestrates deployment to both clouds, handling IAM roles, function creation, API gateway setup, and endpoint configuration. It includes intelligent checks to avoid redeployment if services are already running. The load testing suite. So it contains the quick test. It runs 10 requests per endpoint for rapid validation. Run all test. It executes a comprehensive cold start, warm start, gradual start, and burst load test. Analyze result. It generates the CSV summaries and markdown reports. I've also included the Postman collection templates with pre-configured test for API validation. These scripts are cross-platform compatible with both PowerShell and Bash versions. All the deployments are fully automated and idempotent. The script checks if resources already exist and skip redeployment if endpoint is responding correctly. This saves time and prevents accidental resource duplication. My testing methodology is designed to capture real-world serverless behavior across multiple scenarios. I've implemented four types of load test. Cold start test. After 15 minutes of inactivity, I measure the first invocation latency when the function container is completely cold. This is repeated 5 times with 15 minutes of interval between each test. Warm start test. I have executed 20 consecutive requests to measure performance when the function instance is already initialized and warm. Then is the gradual load test. I've progressively increased the load from 1 to 10, 10 to 50, and 50 to 100 requests per second to observe how each implementation handles the scaling. Burst load test. I've sent 50 concurrent requests simultaneously to test the behavior under sudden traffic spikes. So all the tests use curl-based HTTP request with response time measurement down to the millisecond precision. Every request captures timestamp, status code, response time, and success status, writing results to CSV file for detailed analysis. Uh, so the deployment architecture leverages cloud native services on both the platforms. For AWS Lambda, I have used EU North 1, Stockholm region. Each function is deployed with IAM roles, integrated with API gateway, HTTP APIs for public endpoint, and configured with execution policies. The deployment script uses AWS CLI to create functions, upload code packages, and configure triggers automatically. The Spring Boot function uses a Spring Cloud Function adapter as the handler, while Quarkus uses its native Lambda handler. For Azure functions, I have deployed to the West Europe region under a single resource group called Thesis Performance RG. Each function app uses consumption-based hosting on Linux with Java 17 runtime. These functions are HTTP triggered with anonymous authorizations. Azure CLI handles resources group creation, storage account setup, function app provisioning, and code deployment. Now let me share the preliminary test results from the quick performance test. So as we can see, the fastest cold start was from the Spring Boot AWS, which is 655 milliseconds. The slowest cold start was from the Spring Boot Azure, which is 851 milliseconds. Quarkus on AWS was 722 and on Azure it was 735. So the best performer over here was Spring Boot on Azure at 727 milliseconds on average. And Spring Boot on AWS was 840. 842 milliseconds on an average. Quarkus on AWS was 971 milliseconds on an average, and Quarkus on AWS was uh, and its success rate was all implementation achieved 100% success rate with no failed request. And interesting finding is that while Spring Boot had the fastest cold start on AWS, it also showed more variability. Quarkus demonstrated more consistent performance across request, but higher overall latency on AWS Lambda specifically. Through this research, I've discovered several important technical insights. So the framework differences are like the Spring Boot application package larger jars, typically 30 to 50 MB, due to the comprehensive Spring ecosystem, while Quarkus produces smaller artifacts, which is 15 to 25 MB, thanks to its build time optimization. However, cold start time don't always correlate directly with the package size, JVM initializations, and framework bootstrap play significant roles. Platform differences. AWS Lambda with API Gateway introduces an additional network hop that can add 20 to 50 millisecond latency compared to the Azure functions integrated with the HTTP trigger. However, AWS Lambda showed better cold start performance for Spring Boot, possibly due to the container caching strategies. Both platforms allocate memory proportionally. Our 512 MB configuration provided adequate resource without over provisioning. CPU allocation scales with memory on both platforms. Azure Functions required additional setup with storage accounts and resource group, while AWS Lambda had a more straightforward deployment model. However, Azure's integrated tooling provided better visibility into functions execution. A critical aspect of this thesis is complete reproducibility. I've created a fully automated testing pipeline that anyone can run. In conclusion, this thesis provides empirical evidence for serverless framework and platform selection in Java environments. So the key takeaways over here are like there is no single winner. Performance depends on workload characteristics and priorities. Spring Boot on AWS offers fast cold start but higher warm response times. Spring Boot on Azure provides excellent warm performance but slower cold starts. Quarkus shows consistent performance both but requires careful tuning platform careful tuning. Platform choice matters. Like AWS and Azure have different performance profile. So for cold start sensitive application with infrequent traffic, consider Spring Boot on AWS Lambda. For high throughput warm workloads, Spring Boot on Azure Function performs well. For predictable performance, Quarkus offers more consistent latency patterns. For cost optimization, further analysis of the pricing model is recommended. There are several directions to extend this research. Running a large-scale load test with thousands of requests, then running Quarkus native using GraalVM, which may drastically reduce cold start times. Testing input-output bound workload such as database or external API calls. Exploring different memory CPU settings and comparing cost efficiency. This would help to create a more comprehensive understanding of Java's place in the serverless landscape. Thank you.